Alright, this LeetCode question is called Balanced Binary Tree. It says, given a binary tree, determine if it is height balanced. For this problem, a height balanced binary tree is defined as a binary tree in which the left and right subtrees of every node differ in height by no more than 1. So with this binary tree, just by looking at it, we can see that it's balanced because the left side has a height of 2 and the right side has a height of 3, and we're allowed to have a difference of 1. So that one's balanced. This one is not balanced because the left side has a height of 4 and the right side has a height of 2. So this one is not balanced. Alright, in this video, we're going to go over some definitions/assumptions, and then we'll put them all together to help us solve the problem. Alright, so what is a binary tree? A binary tree is a data structure where each node has at most 2 children. So let's say this node. How many children does it have? It has no children. And by the way, these things, I'm just using them as placeholders for the word null. I don't want to pollute this with the word null, and this is just shorthand for that. All right, so that node had no children. How many children does this node have? It has 2 children, this node and this node. All right, next we'll go into the height of the binary tree. Well, first we have to realize the fact that each node is in and of itself a binary tree. This can be viewed as its own binary tree, so can this, so can this, so can this, and so can this. All right, so what's the height of this binary tree? It's actually pretty debatable. It could either be viewed as 0 or 1. So some people would say this has a height of 0 because it has no children. Some would say that it has a height of 1 because the node itself can be considered 1. It doesn't really matter each way for this problem, so we'll just say that each one of these has a height of 1. So what's the height of this? Well, this has a child, so we consider this to be 1 and this to be 1. So that would have a height of 2. All right, and finally, what height would this have? Notice that on its left side, we have 1, 2, 3, but on its right side, we have 1, 2. So what would the height be? This is very important. The height would be the side with the most children. So in this case, this is the side with the most children, so we'll consider this the height of the binary tree. So this will have a height of 3. The next concept I should point out is very close to what we just did, but just note that if a node is null, we'll consider that to have a 0. So remember we said this has 1, and this has 1, giving it a height of 3. That would mean that every time you see a null node, that is a 0. So this is 0, 0, 0, 0, 0, and 0. All right, so let's get more to the meat of the problem. What exactly is an unbalanced binary tree? An unbalanced binary tree is just a tree that has at least one node whose left and right sides have a height difference of more than 1. And I'll show you what I mean. Remember earlier we said this has a height of 3. So its left side is 3, 1, 2, 3. But in order for us to determine if it's an unbalanced binary tree, we also have to take into consideration its right side. Its right side, like we said, has a height of 2. So the difference between 3 on its left side and 2 is 1. We'll still consider that balanced. It would be unbalanced if the difference is more than 1. So let's extend this binary tree to show you one that's unbalanced. Say this is 7, and that has no children. Now what's the height of the left side versus the right side? The height of the left side is now 1, 2, 3, 4. And the height of the right side, like we said before, is 2. 4 minus 2 is 2. That would be an unbalanced binary tree. And remember earlier I said that if any one of its nodes is unbalanced, the whole thing is unbalanced. So let's do another quick example. And we can start with the bottom since that's more in line with how we're going to solve this problem. So we'll start here. Is this an unbalanced binary tree? The left is 0 and the right is 0, so no, that's not unbalanced. What if we go one level up? Its right child is 0 and its left child is 0 down here and 1, so its left child is 1. 1 minus 0 is fine. That's still considered balanced. Let's go up one more node. How many children does 3 have? It has 0 children on the right. And how many does it have on the left? 0 here. This is considered 1. So is this. So how many children does this have? It has 0 on the right and 2 on the left. 2 minus 0 is 2. Remember, you could have a maximum difference of 1, so this would be an unbalanced binary tree. Don't get confused with how sometimes I'm talking about its children versus its height. It doesn't really matter. The concept is the same. We could have also found the same thing saying this has a height of 1 on the right side and a height of 1, 2, 3 on the left side. Well, it's 3 minus 1, that's 2, so it's unbalanced. All right, so the final tiny concept we have to understand is that we're taking the absolute value of the difference between the left and the right children. What do I mean? So the left side of this has 1, 2, 3, 4, 5, a height of 5, and the right side has a height of just 1. So that's 5 minus 1. That gives us 4. But what if the tree were set up a little differently? What if instead this was the binary tree? In this case, the right side would have a height of 5, 1, 2, 3, 4, 5, and the left side would have a height of 1, so we'd take 1 minus 5. That gives us a negative number. But we can just ignore the negative. So remember, what we have to do is find the absolute value. What's the absolute value of 1 minus 5? It's the same as the answer we just got, which is 4. All right, so the way we're going to solve this is we're going to check the height of all the binary trees. If the height difference between its left and right side is greater than 1, we'll return negative 1 instead. So what we're actually doing is we're first checking to see if its children have a value of negative 1. So because we're using depth first recursion, the first thing that's going to be checked is the left side of the number 5. So that's going to give us a value of 0. And what's the right side? It's a value of 0 also. So when you add 1 for the node itself, its left side is 1, and its right side is also 1. Is that unbalanced? Well, 1 minus 1 is 0, and we're allowed to have a difference of 1, so no, that one is still balanced. So now let's go up one level. What's the height of the left side of the node with a value of 4? Well, its left side has 1 more here, so that would give us a total of 2 for its height. And its right side has a value of 0 here. Ignore this. This should really be moved over to like here, because it corresponds to the number 5. All right, so what's the height of the right side of the node with a value of 4? We have 1 here. So is this unbalanced? Well, its left side has a value of 2, and its right side has a value of 1. 2 minus 1 is 1. That difference is still acceptable because we can have a maximum difference of 1. So let's go up one more level. What's the height of its left side? Well, this is 1, so that'll be 1, 2, 3. And what's its right side? Its right child gives us a 0, so its total right side gives us 1. What's the difference between 3 and 1? Well, that's a difference of 2. If the difference is 2 or greater, we actually know that we have an unbalanced tree. So what this one will return is -1. All right, then it's going to check the right side. The right side is going to give us 0 here and 0 here. So that entire level is going to be 1. So finally it says, is my left or right side -1? And it is. So overall, it'll return -1. All right, so let's get to the code. What LeetCode has given us is a function called isBalanced, which accepts a root. A root is just the entire binary tree. In this question, we're going to assume that if the root is null, then the binary tree is balanced. So we'll say if root is null, we'll just return true. Okay? And the way I'm going to solve this is I'm going to have a helper method which gets me the height of the entire binary tree. And remember I said that if the height on either side is unbalanced, I'm just going to return -1. So overall, I'm just going to check whether the method that I'm going to use is going to return to me a -1. So I'll say return get height of root and see if that doesn't equal -1, because if it does equal -1, that means it's unbalanced, and if not, then we know it's balanced. All right, so let's write the helper method. We know it's called getHeight. So let getHeight equal the function, which will accept a node. Remember, each node is itself a binary tree. And we know that if the node is null, it'll return a 0. So if node is null, we'll just return 0. And we know we're going to use recursion, so we'll recursively find the height of the left and right nodes. So we'll say let left equal getHeight of node.left, and we'll say let right equal getHeight of node.right. So because of the way we've set this up so far, the first thing it'll check is here. This is going to be 0, and this is going to be 0. Now we'll check whether or not that's unbalanced. So we know that if either the left or the right is unbalanced, we have an unbalanced tree. And I mentioned earlier, I just haven't put this in the code yet, that if it is unbalanced, that it'll have a value of -1. So we'll check if left equals -1 or right equals -1, then we'll return -1. All right, as I'm editing this video, I realize I might not have been clearer what this line means. When I'm talking about left and right, it's talking about the heights of the children I've already calculated. So if either one of them is -1, meaning if any one of my children is unbalanced, then I'm going to be unbalanced. And I'm going to pass that -1 all the way up to the top. So now every node above me is also going to have a value of -1. Why else would we return -1? We'd return -1 if the absolute value of the difference between the child nodes is greater than 1. So we'll say, or math.abs left minus the right is greater than 1. I know I've said it a bunch of times before, but I'll say it again. That's because to be balanced, we can have a maximum difference of 1. So that's just checking to see if the absolute value of the difference is greater than 1. And if it is, we know it's unbalanced. So we'll return -1 to signify that. But if we've gotten past that step, we know that it's not unbalanced. So now we'll just return the maximum of the left and right children. So left and right, and we have to add 1 to the height. So this is the entirety of the code right now, but I'll just walk you through all of the code using the binary tree on the left just to show you exactly how it works. All right, so as we said, it starts all the way at the bottom left. That has a value of 0, and the right side has a value of 0. So it'll return the maximum of those two. What's the maximum of 0 and 0? It's 0 plus 1. That's what's happening on line 32. So here would be a value of 1. Then we get bumped up a level. On line 21, it asks if the node is null. It's not, so we go to line 25. Line 25 gets the height of the left node. We know the left node is 1. Line 26 gets the value of the right node. It asks if the node is null. Yes, it is, so that half will return 0. Then it'll check on line 28 if either the left or right children is a -1, meaning we already know it's unbalanced, and no, it's not, or the difference between the two is greater than 1. The difference between the two is 1 minus 0. That's not greater than 1, so it goes to line 32, and it adds 1 to our height. So our height right now is 2. Then we get bumped up 1 level. It asks if the node is null on line 21. No, it's not. On line 25, it says, get me the height of the left child. We know that's 2. On line 26, it says, get me the height of the right child. So it goes back to line 21 and checks if that node is null. Yes, it is. So then it returns 0 on line 22. So now we know the left side is 2 and the right side is 0. So it checks. Is the left side -1? No, it's 2. Is the right side -1? No, it's 0. Is the absolute value of the difference between those two greater than 1? 2 minus 0 is greater than 1. So in this case, we'll return -1. So now we're bumped up 1 level to the node with a value of 1, the very first node. Is that null? No. Line 25 retrieves the value of the left node, which is -1. Then it's going to check the right side. So because of recursion, that would put us here. The left side of this is 0, the right side of it is 0. So it's going to see if that's unbalanced. No, it's not. So line 32 is going to add 1 to this. So the value of this is 1. So now we know the value of the children of the left and right halves of the top node. The left is -1 and the right is 1. So when we get to line 28, it says, if left is -1, is it? Yes. So it immediately returns that this is also -1. So now there are no more nodes to check, so we get kicked out back to line 17. And that says return whether or not this doesn't equal -1. It does equal -1, which means that this is unbalanced. All right, so let's run the code, see how we did. All right, accepted, let's submit. All right, so it's saying our code is faster than about 27% of other JavaScript submissions. As usual, the code and written explanation are linked down below. If you liked the video, give it a like and subscribe to the channel. It helps out a lot. See you next time.